for our final talk of the early morning session. We have Daniel Roca González, who will be talking about hyperuniformity of hat tilings and inflation tilings. So, again, some things which are hot off the press.
Yes. Okay. Yeah. Great. Okay, so welcome to my talk, and thanks for allowing me to be here. Okay, so I want to talk about hyperuniformity, and in particular of hat tilings. So my goals are twofold. First, there is this weird term, which is hyperuniformity. This is a property tilings and point processes can have. I want to give you a feel for what that is. And also I want to convince you that hat tilings are hyperuniform, and this puts it in equal footing with many other inflation tilings and aperiodic tilings. Okay, so first on aperiodic order and hyperuniformity. First, we are interested in structures which have some kind of aperiodic order. So they are not periodic, they are not lattices, but they still have some kind of order, which when we look at how they look in the long range. And there are several ways to construct stuff that has this property. And so we can use local rules like we just saw. We also have cut and project sets. They are a very important family. And we also have inflation tilings and rules which play an important role for the hat tiling. In fact, hat tilings can be put in all three of these methods, but today I will be interested in inflations. And I want to say that hat tilings have some kind of long-range order, but what does that actually mean? There are several properties that can be considered to be ordered without being periodicity. One of them is finite local complexity. You have a finite amount of patterns that pop up over and over, and you can look at how many of these you get when you look at bigger and bigger parts. I believe we will have a talk about that later. A very important thing is pure point diffraction, which will come up later. But the thing I will care about most today is something called hyperuniformity, which was a concept invented by Torquato and Stillinger in the 2000s. Okay, so let's look. This is a hat tiling. We're all seeing it. We want to somehow say something about the styling. So one thing we can do is, okay, we look at the circle inside of the hat tiling, and we want to see how the hat tiling looks here. And okay, what kind of question we can ask? One possible question is, okay, how many tiles fall inside this circle? Maybe also how many dark blue tiles, how many light blue tiles, whatever. The answer to this question is, well, it depends. Why? Because, this is, I put one circle there and this particular hat tiling, but maybe I could put the circle here or someone else. So maybe this is not such a good question. A possible better question is, okay, how many tiles do we have on average? So if we move this circle of this size around, how many tiles or maybe blue tiles, whatever, will we get on average? This is something that is called frequency, and people have looked at a lot for many tilings. It will crop up later. But another thing we can ask is, okay, how much does the amount of tiles vary when we move this circle around? This is something called number variance. So how does the number of tiles vary when I move around the hat tiling? And to get a feel for how this should behave, I'm going to look at two examples of structures we understand well. First of all, these are points in a Poisson process, which I don't want to explain exactly what that is, but it means we're placing points as randomly as possible, no order at all. So I've chosen this so that there we should have 50 points on average inside the circle, but this, as you can see, this varies a lot. Like maybe I have 48, maybe I have exactly 50, but maybe I have 64, whatever. And we can see this is because of, okay, at any point, maybe I have this part that has no points at all, or maybe I have one small part where I have a lot of points because it's all completely random. And the complete opposite is the case of a lattice. Here I have the points basically as orderly as one can have them, and I'm moving the circle around. And it's still not exactly the same amount of points, but you can see it varies way less. It's maybe 52 or 57. We don't get 64. And the way to understand this is that if I have a Poisson process, at any point in the circle, something can go wrong. I can get too many points or too little points. So we expect the variance to grow with the volume of the area of the circle. But if we have a lattice, then the only thing that can vary is when I'm near the boundary of the circle, which points get included and which don't. Maybe if I move the circle a bit, some point disappears or appears, but if we are inside the circle, there's a very clear relationship between the area of the circle and the points. So the variance only comes from the boundary. And this motivated Torquato and Stillinger to define hyperuniformity. We say that a random set of points is hyperuniform if the variance grows slower than the volume of a ball. So we're letting the radius of a ball to go to infinity, and if the variance grows slower than R to D in this sense, then we say it's hyperuniform. For tilings, we can do something basically the same. Maybe we also care about hyperuniformity for individual colors of individual kinds of tiles. And then the intuition is that if the variance grows with the volume, this is random. So if it grows slower than that, there is some kind of order to the points. And people have looked at it for some examples. Also, people in this room have looked at it. So if there are Torquato and other people already studied this from inflation tilings in one dimension, and also there were proofs that by Baake, Grimm, and Gela. And if you can look at this a bit more systematically for at least certain Cartan project sets. But actually the reason physicists and other people were very excited about this is that there are certain states of matter which are not quasicrystals at all. They're models of like gases or liquids, but they still have this hyperuniformity property. So this is something that lies outside of what one would consider to be order classically. But even for quasicrystals, it's not actually a given that they will be hyperuniform. From the picture I showed you before about the lattice, you would be forgiven to think, okay, if I have a set of points that is where the points are evenly spaced out, and maybe then surely it should be hyperuniform, but this is not the case. Even Torquato already had some examples of 1D inflation tilings where we have anti-hyperuniformity, so the variance is even bigger than in the Poisson case. And recently, Björklund and Hartnig showed that there are even cut and project examples, so quasicrystals that are still anti-hyperuniform. So how can we determine if something is hyperuniform or not? There are several ways, but one important tool is diffraction. Diffraction is a very important thing in the quasi-crystals were discovered because they had a peculiar diffraction pattern. But the reason we will care is that we can see hyperuniformity by looking at the diffraction measure. Namely, if I have a set of points or a tiling, then we can say it is hyperuniform if the decay of the diffraction around the origin is fast enough. So if, for example, if the in 2 dimensions, if the decay is 1 times faster than the dimension, then we get the variance is 1 less. So it's a hyperuniform. And the thing is, the variance stops at r to the d minus 1. So if we have a lattice, the variance is proportional to the boundary, and this is one can show that we can get less than that, but the decay, this spectral hyperuniformity can go on way farther than that. And if the decay is very, very fast, then we get this gives you even more order in the set. This gives you rigidity properties. And to see for some stuff that is known and also have been able to show, it's Baake, Grimm, and Gela were able to see that the Fibonacci tilings in 1 dimension are hyperuniform, where the decay in the spectral part is r to the 4. There was already a paper by some physicists where they showed that the Penrose and octagonal are also hyperuniform with power to the 8, and also extending the methods of Baake, Grimm, and Gela, I have been able to show that many other inflation tilings in several dimensions are hyperuniform. And in particular, we will see that the hat is a bit different, but it's still hyperuniform. Okay. But before we get to the hat tiling is special because it's not actually an inflation tiling in the classical sense. So I will explain how this works for Penrose tilings first. So the one way to define at least a form of Penrose tiling is using this inflation rule, using half kites and half darts, so these 2 kinds of triangles. What we're doing is we have this scaling constant, which is the golden ratio, and each step we are making all the triangles go a bit bigger and then covering each triangle with the smaller triangles again. And we do this always in exactly the same way. Here the colors are important because the darker triangles are being reflected, and this is important when we apply the rules several times. Because when we have this rule, okay, we can do this over and over, and as we do it more and more, we get more complicated patterns. And this is how we get, if we do this with, one has to show that this can be built to a whole tiling, but in the Penrose case or something like this, it works. And a very important quantity when studying inflation rules is the inflation matrix. This is a matrix that counts how often each tile appears in the inflation of each tile. So for example here, we see that the inflation of the half kite has 2 half kites and 1 half dart. And for the half dart, it has one of each. So we put this matrix that is 2, 1, 1, 1. And This one thing that we can do with this inflation matrix as a flavor of the kind of results we can do is count frequencies, which is already interesting. So if we have a big part of a Penrose tiling, how often will we have half kites and half darts? And it turns out that this is a certain eigenvector of this matrix. Why? Because the idea is if I take a whole Penrose tiling and I apply the inflation rule once, we get something that looks pretty similar. It will be not exactly the same Penrose tiling, but it will still be a Penrose tiling, so it will have the same frequencies. But okay, what are we doing when we do an inflation? We're scaling everything so the tiles get more sparse, but also we're substituting its triangle with several triangles, which is so we're putting more triangles according to this inflation matrix. And this means that the vector which has the frequencies has this equation, which is the eigenvector equation in this case. This general idea is what is called normalization. So applying one step of the inflation gives you large scale structure, which is the same as the small scale structure. But there is one subtlety here that I haven't considered. I have said that Penrose tilings only have two kinds of tiles, but this is only because I've been rotating them and translating them and reflecting them. But sometimes people will rather use only translations, and in fact the problem with rotations and reflections is that they don't commute, so they make the theory more difficult. So if you open a textbook on inflation tilings, they will probably define it with translations first, and they maybe later they say, okay, the theory works similarly if you do also rotations and reflections. This usually works, but there are some things that get more complicated, and in particular when it gets to diffraction, we run into a problem, which is that we don't have it's not so clear what it means to take the Fourier transform of something in the group of isometries. It's that's usually rather for abelian groups. Okay, so I said that there was already work on hyperuniformity of inflation tilings. This is what this means. It's not quite for one dimension, but it only works with translations, and we will see why that's a problem. And this tells us that the hyperuniformity like the decay of the diffraction around the origin depends only on the inflation matrix, and namely on the first and the second eigenvalue. So it's similar, the idea is similar to what we just had for the frequency. It's a bit more complex because now instead of having just two numbers, the diffraction is a measure, but it's the same core idea. It does work only for when we have pure point diffraction, but those are most of the known examples. And for example, this shows that Fibonacci tilings in one dimension and Silvermeer tilings in one dimension are hyperuniform, which is already an interesting result. But if we try to apply this to Penrose tilings, we run into a problem, which is that theorem uses translations. So we have to consider each copy of the triangles as a different prototype. And not only would we rather not work with a 40 by 40 matrix, but also it turns out that the theorem kind of breaks down or doesn't work as well because the second largest eigenvalue is tau, the golden ratio. And the theorem works especially well when the gap between the first and the second eigenvalue is as big as possible. Here, this is not enough even to get a high hyperuniformity. It's just in the boundary where you don't get it anymore. Okay, and this is what recently I was able to fix. It's the same version of the theorem, but in several dimensions we are allowed to use the reduced matrix. And then it does work for the Penrose tiling, where the second eigenvalue is only tau to the -2, which is very small. And what is going on? I mean, their proof was by showing a renormalization of the autocorrelation of the tiling using relative frequencies, and then you could zoom in to the origin. You got something in terms of matrix cocycles, which is kind of like the eigenvalue stuff before, but more complicated. And the secret sauce, if you want this to work well for stuff like the Penrose tiling, where we have symmetries, is we want it to work in this non-abelian group, and then instead of using classical diffraction, we use something called powder diffraction or spherical diffraction, which is a version that works well in the setting. And then their argument goes through in a very similar way. Okay, but this is the Penrose tiling. I promised you had tilings. Before that, I will show you this inflation rule, which was first found in a paper by David Smith and some other people you may also know. Yes, it's not quite the meta-tiles of the hat tiling, and this is a bit different from the Penrose rule because I'm not covering the scaled tiles exactly. But we are still moving the tiles in the same way, always. So it's the same theory still works. And in particular, it has been shown that it has a pure point diffraction. Then the scaling constant is the square of the golden ratio. And then if we look at the matrix, then we get that the second eigenvalue is 1. So this is not quite as fast as in the Penrose case, but it's still more than enough to tell us that these cap tilings are high hyperuniform. And then, okay, so this is a hat tiling, and as we have already seen yesterday, it can be partitioned in these kinds of metatiles. So these 4 tiles, those are not exactly the same as the inflation rule I just showed you before, because the gray ones are slightly narrower. But it turns out that this is not a big deal, because what we're doing is we're doing a deformation. We're taking these gray tiles and we're adjusting them a bit. And then it has been shown that by Baake, Geller, and Saddon, that this doesn't make it too broken. It's still conjugation. It's equivalent as the dynamical systems, and in particular, this means we're only shifting the tiles by a bounded amount, and then we don't get. If we look at the diffraction, something gets lost. But if we look at the variance of this of this number variance, it's still going to be linear, so faster than the volume of the balls. And this is the thing we wanted. Later we will have a talk by Lorenzo where they explain in more detail how this what the relationship between these two things are. And yes, so this is the thing I promised. So thanks for listening.
Any questions? Yes? Lorenzo?
More of a comment than a question. I mean, this results really relies very much on the fact that everything is done in a rotationally invariant way. If you want to see what the fluctuations are in the number of something, of a pattern, not just a tile, which you can do for any pattern, that is, you do it in, say, you keep track of the tiles in this orientation minus the number of tiles in this orientation. If you do something in a rotationally non-invariant way, then you pick up eigenvalues of the larger matrix. And actually, it isn't even the matrix of substitution on tiles, it's really the matrix of substitution on the second cohomology. I know, you're allowed to run screaming from the room when somebody mentions cohomology, but that turns out to be the thing that controls it. And a property of the Penrose tiling, which is also a property of the Hat tiling, which is also a property of the Spectral tiling, is that there is a non-rotationally invariant eigenvector with eigenvalue that is the stretching factor as opposed to the square of the stretching factor. And what that means is that the fluctuation, you can find regions in which the population of the particular pattern that you happen to be looking at varies from its overall average by perimeter times the log of perimeter. So the fluctuations go a little bit faster than perimeter, which means the variance goes a little bit faster than volume, well, area, which is exactly what Daniel was telling us. Okay. If you only do it with rotationally invariant things, the second eigenvalue is very small, and you get hyperuniformity. If you break rotational invariance and start looking at patterns where you keep track of which way things are pointing, then the hyperuniformity falls apart. And it isn't just that the theorem wasn't sharp enough, it's that it really fails that the fluctuations go as perimeter log perimeter.
Yes, that's a very good comment.
Any other questions or comments? That?
Yeah, I was just wondering what happens if you have infinitely many tile rotations, like the pinball tile?
That's a good question. Actually, the theorem would still work in the sense that if you look at the rotation invariant patterns, then you could actually apply that theorem. The problem is that for the theorem you need a pure point diffraction. And I'm not sure if that's, you need a pure point powder diffraction, which maybe could be true, but in the infinite rotations case, I don't know any good examples where you have that. For example, I believe for the pinwheel inflation, which is the most common example with infinite rotations, I believe it's still open, and I think the conjecture is more on the side of it not being a pure point diffractive.
Thank you very much. Other questions? Okay, if there are no other questions, let us thank the speaker once again.